In this video, we are going to learn some of the most important definitions from Advanced Algebra 1. Okay, so here, let me start from the definition. Second, dual of V. Okay, it means for any vector space V, consider any vector space. The name of the vector space is V. The dual V double cap, okay, of V, it means second dual of V is denoted by V double cap. Okay, for any vector space V, the dual V cap of V cap is called second dual of V. Okay, so for example, if V cap, the value of V cap is this, that is V cap is equal to homomorphism of V comma F, then V double cap is written like this, homomorphism of V cap comma, if V cap is this, then V double cap is this. So that is V double cap is equal to homomorphism of, substituting the value of V cap here. So what is V cap? Homomorphism of V comma F. So here substituting that value comma this F. So this is the definition of second dual of V. Okay, and let us pass on to the next definition, that is annihilator of W. Okay, so if W is a subspace of V, so here you have a vector, that vector space, that is V. Okay, from the vector space you are choosing a subspace, that is denoted by capital W. So if you want to say this W as an annihilator of W, if it is in this format, okay, so let me read that. A of W should be like this, that is A of W is equal to F belongs to V cap, that is from V cap you have to choose an element, that is F, such that it's a function. Okay, so F of W, small w equal to 0. For all this you have to choose this small w from the small w is an element from capital W. Okay, so this is the definition of annihilator of W. So let me repeat, A of W is equal to F belong, that is what should you remember is just keep this in your mind, and from this you have to know F is from where and W is from where. Okay, all these you have to know, but only thing you have to memorize or you have to store in your mind is F of W is equal to 0. If anybody asks you what is mean by annihilator of W, the only thing that should pop up in your mind is F of W is equal to 0. So if you can recall this, then you could answer that question in a perfect manner. Okay, F of W equal to 0. So here is F is from V cap and W is from the subspace W. Okay, now let's move on to the next definition, that is inner product spaces. This is also a very important definition. So let me read the definition. The vector space V, first you are taking a vector space that is denoted by capital V over the field F. Okay, from the field F you are choosing a vector space capital V. So this vector space is said to be inner product space if it satisfies some of the conditions. Here you can see those conditions. Okay, so let me read the conditions. Inner product U comma V is equal to inner product V comma U the whole bar. Okay, just interchanging the places of the terms, right? Here U comma V, here you are writing V comma U, and the bar is must. Okay, that is the first condition. This condition should be satisfied. And also the second condition is inner product U comma U greater than or equal to 0. Okay, inner product U comma U should be greater than or equal to 0, and they are saying U comma U will be 0 when this U comma U will be 0 if and only if U equal to 0. If the value of U is 0, then U comma U will be 0. Now the third condition is alpha U plus beta V comma W. Okay, inner product alpha U plus beta V comma W is equal to, first write the alpha, then the element that is near to alpha, that is U, right? Then inner product U comma this W. Okay, plus this plus, then beta, this beta, what is the value near to beta, that is V, right? So beta of v, this v comma w. This is how you have to write the conditions. So here you have you are choosing the elements, right, like u, v, right? That's it. This u and v are from the vector space capital V, and here are two scalars, right? What are the scalars? Alpha and beta. U, v are the vectors, okay, because you are taking it from the vector space. So u and v are the vectors, and here alpha and beta are there. This alpha and beta are called scalars because you are choosing this alpha and beta from the field F. Okay, I hope you understood this definition. Now let us pass on to the next definition, that is the next definition is orthogonal to V. Okay, orthogonal to V. That is, you are choosing two. Sorry, is that visible now? Yes. Okay. So if u comma v belongs to capital V, that is, you are choosing two elements or two vectors from the vector space capital V. Okay, that they are u and v. Then this u is said to be orthogonal to this v. If you want to say this u, the elements that you are chosen from the vector space V. Okay, so if you want to say two elements you are choosing, so if you want to say one element is orthogonal to the other, if it satisfies one condition, what condition it is? Inner product u comma v should be 0. Okay, if inner product u comma v equal to 0, then you can say this u is orthogonal to v. Okay, I hope you understood this definition. Now let us pass on to the next definition, that is orthogonal complement of v. Sorry, orthogonal complement of w. Okay, so here is a question, what is w, right? So here what you have to do is you have to consider a vector space. The vector space is capital V. Okay, the subspace of this vector space is w. Okay, now the orthogonal complement of w is denoted like this. Okay, the orthogonal complement of w is denoted like this, is defined by, okay, that is, the elements in orthogonal complement of w will be like this. That is, w orthogonal complement of w is equal to set of all x belongs to v, such that x inner product x comma w is equal to 0. So here if someone asks you the question orthogonal, what is orthogonal complement of w, then the only thing you have to memorize in your mind is just memorize this: inner product x comma w is equal to 0. Okay, and from this you have to know where you are choosing this x and where you are choosing this w. All these things without memorization, if you understand that, then you can say. So here you are choosing this x from the vector space V and w from the subspace W. This w from the subspace this w is an element from the subspace capital W. Okay, so this is the definition for orthogonal complement of w. So what is the only thing you have to keep in your mind? Inner product x comma w equal to 0. Nothing else is here to memorize. Okay, if you memorize all these sentences, entire sentence, then there is a chances that you may forget. Okay, in a very limited period of time, within a very limited period of time. So if you want to keep this in your mind for a very long time, what you have to do is just memorize this, fix this in your mind, so that you can give the definition for orthogonal complement of w. Now let us pass on to the next definition, that is orthonormal set. Orthonormal set. Okay, so here you are considering you have a vector space, okay, that is capital W. So from this vector space W, you know that the elements from the vector space will be the vectors. So here what you are doing is you are not choosing one or two elements from the vector space. Here what you are doing is you are taking a set of vectors from this vector space. That is what here they have written. The set of vectors is denoted like this. Okay, in vector space capital V is an orthonormal set. If you want to say this set of vectors as an orthonormal set, if there are two conditions, this two conditions should be satisfied. Only then you can say the set of vectors that you are choosing from a vector is an orthonormal set. So let me read the conditions. First one, Vi, okay, that is any vectors if you are choosing choose any vectors, okay, from the set of vectors. If I choose a vector v1, that is the inner product space of v1 and v1 should be v1 comma v1 equal to 1. That is the first condition. Okay, what is mean by that? From the set of vectors you are choosing one vector, that is v1. Consider like this. So if I write the inner product space of this v1 comma v1, then I should get the length should be 1. If I get this answer, if I get this answer, the one condition, the first condition to say some set of vectors as an orthonormal set is satisfied. And what is the next condition? For I not equal to j, that is you are taking two vectors from the set of vectors. That is, for example, if I choose v1 comma v2, the length I should get 0. Okay, so if these two conditions are satisfied, then I can say that particular set of vectors from the vector space capital V is an orthonormal set. Okay, and let us pass on to the next definition, that is we have completed almost from the unit 1. We are going to complete all the definitions, important definitions. This is the last definition that we can see from unit 1. Okay, these are the most important definitions that you can see in advanced algebra, first unit of advanced algebra. Okay, I hope you got it now. Okay, our definition is modules. Okay, so here what you have to do is you have to consider a ring. Okay, let R be a ring, a non-empty set M. You are taking a non-empty set M. Okay, if you want to say this non-empty set M as an R module, what is mean by R module? What is mean by R? They are denoting a ring as R. Okay, that's why R module. Okay, if you want to say a non-empty set M as an R module, it should satisfy some of the conditions. So let us have a look at that conditions. First, this non-empty set should be an abelian group. Okay, under addition. Okay, this is the first condition, and then these three conditions should be satisfied. They are R of A plus B is equal to RA plus RB is the first condition, and the second condition is R of SA is equal to RS into A. And the third condition is R plus S into A is equal to RA plus SA. Okay, so here this R and S, you have two elements R and S, right? Here R, S. This R and S are the elements that you are choosing from the ring R, and you have A and B here, right? Right? These conditions are with a combination of R, S, A, B, right? So here R and S are the elements that you are choosing from the ring R, and A and B are the elements that you are choosing from the non-empty set M. So if all these conditions are satisfied, then you can say this non-empty set M as an R module. So this is the last definition of last definition from the unit 1 of advanced algebra. So thanks for watching.